Hello everyone, I am Bireshwar Roy. I am pursuing my PhD in the Department of Physics, Indian Institute of Science, Bangalore, in the field of experimental condensed matter physics. In this video, I will be discussing the solutions of one question from the topic Quantum Mechanics came in the exam GATE Physics 2015 and another question on quantum mechanics came in the exam GATE Physics 2016. This question was asked in the GATE Physics paper 2015. This is a numerical answer type question having 2 marks. The topic of the question is quantum mechanics. The question is, let the Hamiltonian for two spin-half particles of equal masses small m, momenta p1 vector and p2 vector, and positions r1 vector and r2 vector be h equals to 1 by 2m times p1 square plus 1 by 2m p2 square plus half of m omega square times r1 square plus r2 square plus k sigma 1 dot sigma 2, where sigma 1 vector and sigma 2 vector denote the corresponding Pauli matrices. H cut omega equals to 0.1 electron volt and k equals to 0.2 electron volt. If the ground state has net spin 0, then the energy in electron volt is, so we have to find the ground state energy for this given Hamiltonian of this system. Let us see how to solve this problem. So, according to the question, the given Hamiltonian for two spin-half particle system is p1 square by 2m plus p2 square by 2m plus half m omega square times r1 square plus r2 square plus k sigma 1 vector dot sigma 2 vector. Here sigma 1 vector and sigma 2 vector denotes the corresponding Pauli matrices. So, in the Hamiltonian, the first three terms, that is p1 square by 2m plus p2 square by 2m plus half m omega square times r1 square plus r2 square. These three terms is basically denoting the two spin-half particles in three-dimension quantum harmonic oscillator potential. So, for this part of Hamiltonian, we know what will be the energy eigenvalue. The only thing we are concerned about, that is k times sigma 1 dot sigma 2 vector. So, what will be the energy eigenvalue for this term? So, let us evaluate this. For this, what we will do, we have total total spin, that is sigma vector equals to sigma 1 vector plus sigma 2 vector. Here sigma 1 vector is the spin of first spin-half particle and sigma 2 vector is the spin for second spin-half particle. So, we will take the dot product on the both side with sigma. So, we will get sigma dot sigma equals to sigma 1 plus sigma 2 whole square. So, sigma square equals to sigma 1 square plus sigma 2 square plus 2 times sigma 1 vector dot sigma 2 vector. So, from here we can get sigma 1 vector dot sigma 2 vector equals to half of sigma square minus sigma 1 square minus sigma 2 square. So, we have the Hamiltonian p1 square by 2m plus half m omega square r1 square. So, this is the three-dimensional simple harmonic oscillator potential for the first spin-up particle, and similarly for the second spin-up particle we will have this three-dimensional quantum harmonic oscillator potential, that is p2 square by 2m plus half m omega square r2 square, and the spin-spin coupling term we have rearranged it as k by 2 times sigma square minus sigma 1 square minus sigma 2 square. So, we are denoting this term as H1 and this two term as H2. So, H1 and H2 are basically Hamiltonian for the three-dimensional quantum harmonic oscillators, and the last term, that is spin-spin coupling term, that can be written as k by 2 times 2 by h cut whole square times s square minus s1 square minus s2 square, because we can relate this spin operator and the Pauli matrices by this relation, s vector equals to h cut by 2 times sigma vector. So we have the Hamiltonian, that is h1 plus h2 plus 2k by h cut square times h square minus h1 square minus h2 square. So here h1 and h2 are Hamiltonian of a spin half particles in three-dimensional quantum harmonic oscillator. So the energy eigenvalue will be E equals to N1 plus 3 by 2 times h cut omega plus N2 plus 3 by 2 times h cut omega plus 2k times s into s plus 1 minus s1 into s1 plus 1 minus s2 into s2 plus 1. So here actually the eigenvalue for a square will be s into s plus 1 times h cut square. So for that h cut square, that will be cancelled out with this h cut square in the denominator, and that's why we are getting this term. And for the first two terms in this energy eigenvalue is basically the energy for the three-dimensional quantum harmonic oscillator. Here N1 consists of three principal quantum numbers, that is nx plus ny plus nz. So we are denoting for the first particle, that is nx1 plus ny1 plus nz1, as N1, and similarly for the second particle, that is N2. Now in the ground state, the three-dimensional quantum harmonic oscillator will have the nx equals to 0, ny equals to 0 and nz equals to 0, and n1 and n2 are the summation of the x, y, z components, so both will be 0. And according to the quotient, total spin is 0 at the ground state. But S1 and S2 is equals to half because they are spin half particle. So we'll put these values in the ground state energy eigenvalue. So we'll get 3 by 2 times h cut omega plus 3 by 2 times h cut omega plus 2k times 0, because total spin is 0 at the ground state, and for S1 equals to half and S2 equals to half, we will get minus half times half plus 1 minus half times half plus 1. So from this we will get ground state energy eigenvalue, that will be 3 h cut omega minus 3k. Now it is given that h cut omega equals to 0.1 electron volt and k equals to 0.2 electron volt according to the question. So we'll put these values in the ground state energy eigenvalue. So we'll get ground state energy eigenvalue EGS equals to 3 times 0.1 minus 3 times 0.2 electron volt. So effectively we'll get the final answer, that is energy eigenvalue of the system is minus 0.3 electron volt. So for this given Hamiltonian at the ground state, energy will be minus 0.3 electron volt. This question was asked in the GATE Physics paper 2016. This is the MCQ question having 1 mark. The topic of the question is quantum mechanics. The question is, the scattering of the particles by a potential can be analyzed by Born approximation. In particular, if the scattered wave is replaced by an appropriate plane wave, the corresponding Born approximation is known as the first Born approximation. Such an approximation is valid for option A, large incident energies and weak scattering potentials, option B, large incident energies and strong scattering potentials, option C, small incident energies and weak scattering potentials, and the last option, option D, small incident energies and strong scattering potentials. So let us see what is the correct option for this question. So we will discuss about the scattering theory in quantum mechanics in details, and we will get into the solution part. Before going to the main part of the solution, we will be discussing some important concepts regarding scattering theory in quantum mechanics, which will be highly useful to solve this problem. Then let us start. Let us consider a beam of particles having each of mass small m. They are traveling along the z-axis with some velocity v. Now we will be considering the incident particles as free particles. So the particle wave will be incident plane wave, and the plane wave will have a wave vector k naught. Now the incident particles will be scattered by scattering potential or target potential V. This target potential may come due to the target material kept at the origin or at the center. Now when the incident particles will reach near the target potential, they will experience a force. Now the range of the scattering force will be effective up to a distance r0. So this effect of the scattering potential will remain in the sphere having radius r0, where r0 is known as range of scattering potential. Now, due to the interaction of the incident particles with the scattering potential, the particles will get scattered in all the directions. After leaving the sphere, the incident particles move again along a straight line. So basically, when the beam of particles will be within this sphere of radius r0, they will feel the effect of target potential. So they will experience a force and they will get scattered. But when after scattering, they will come out of this sphere, they cannot experience the effect of target potential there. So they will act as free particle outside this sphere of radius r0, and they will move along the straight line. The angle between initial and the final straight line is known as scattering angle, that is denoted by theta here. Now after scattering, all the particles will be scattered in all possible direction in the sphere. So we will be considering a small region, basically a small differential solid angle d omega, through which the some particles are getting scattered. So the cross section through which some particles are getting scattered is dA equals to r square time the differential solid angle d omega, which is shown here by the dark region. So through this differential area dA, the scattered wave or particles will be scattered in d omega along theta and phi direction in the 3-dimensional spherical polar coordinate. Till now, we have already seen when some incoming particles are reaching near the target potential or scattering potential V kept at the origin, the incoming particles will experience some scattering force due to the target material or target potential, and they will get scattered. So this scattering phenomena is basically happening due to the collision between the incoming particles and the target material. So this collision may be considered as two types depending on the phenomena. The two types of collisions are elastic or inelastic. Now the total number of collisions over the duration of the experiment is proportional to, first one is total number of incident particles, and second one is number of target particles or target potentials per unit area in the path of the beam. Now the number of particles scattered into an elementary solid angle d omega equals to sine theta d theta d phi is proportional to a new quantity, that is differential cross section, and mathematically that is denoted by d sigma d omega as a function of theta and phi in spherical polar coordinate. Now let us see what does it mean by differential cross section d sigma d omega. So it is defined as the number of particles scattered into the elementary solid angle d omega, that is sine theta d theta d phi, in a direction theta comma phi per unit time and per unit incident flux. Now, the incident flux means the number of incident particles per unit area per unit time. Till now, we have already discussed about the differential scattering cross section d sigma d omega in a scattering experiment. And also we have discussed the definition for the differential scattering cross section. From the definition, we can construct a mathematical relation between the d sigma d omega and the incident flux, that is J in, and the number of particles scattered into elementary solid angle d omega, that is dn, as a function of theta comma phi. So this mathematical equation tells us d sigma d omega as a function of theta comma phi equals to 1 by J in times dn d omega as a function of theta comma phi. Here J in is the incident flux, that is number of incident particles per unit area and per unit time, and dn as a function of theta comma phi is the number of particles scattered into the solid angle, elementary solid angle d omega, that is sin theta d phi in a direction of theta comma phi in the spherical polar coordinate per unit time. Now, if we know this differential scattering cross section in a scattering experiment, then we can calculate the total scattering cross section in that experiment. And this total scattering cross section is given by sigma t equals to integration of d sigma d omega over the entire solid angle. So this integration will run for theta and phi, and theta ranges from 0 to pi and phi ranges from 0 to 2 pi in this spherical polar coordinate, and inside the integration we will have d sigma d omega times d omega will give this term sin theta d theta d phi. Now we will consider a special case. Our scattering potential is spherically symmetric. If we consider our potential is spherically symmetric, then for that the d sigma d omega will be only the function of theta. So d sigma d omega will not depend on the phi term. Hence our total scattering cross section will also be the function of theta only, not phi. So for the special case, this total scattering cross section sigma t will be 2 pi times integration over theta equals to 0 to pi d sigma d omega as a function of theta sin theta d theta. Here 2 pi is coming for the integration of phi from 0 to 2 pi. Now the dimension for the differential scattering cross section and the total scattering cross section is area, and the typical unit used for this scattering cross section is barn. One barn is basically equals to 10 to the power minus 28 meter square. Now we'll be discussing briefly about the scattering amplitude. So basically, what will be the amplitude of the scattered wave when an incident particle beam or particle wave is getting scattered out due to the target potential or target material. At large distances from the scatterer, the effect of scattering potential is negligible. That we have already seen in the first slide. So basically there will be only the effect of scattering potential on the particles within some scattering potential range or not. Otherwise the particles will not feel the effect of scattering potential. The parallel beam of incident particles can be represented by the free particle equation, that is plane wave equation, that is given by psi incident as a function of r vector equals to a times e to the power I k naught dot r vector. Here k naught is the wave vector for the free particle wave. Now, as the particle beam is moving along the z direction, we can write the wave function for the incident particles as psi incident as a function of r vector equals to a times e to the power I k naught z. So this is the equation of plane wave moving along the z direction. Now, before the interaction with the target, the particles with incident beam are independent of each other and they move like free particles with the momentum h cut k naught vector. Now, when the incident wave collides with the target material, an outgoing wave is scattered out. In case of isotropic scattering, this scattered wave will be spherically symmetric. So then we'll have the scattered wave in the form of a times e to the power I k dot r by r. But in reality, the scattered wave is not spherically symmetric. Its amplitude depends on the direction theta comma phi along which it is getting scattered. Therefore, the actual scattering wave function is given by psi scattered as a function of r vector equals to a times scattering amplitude function, that is f theta as a function of theta comma phi times e to the power I k dot r divided by r. This is a spherically diverging scattered wave, and this f as a function of theta comma phi is known as scattering amplitude. Now, for the case of spherically symmetric potential, that means our scattering potential only depends on the distance from the center, that is r, then our scattering wave function can be written as a times the scattering amplitude as a function of theta, that is f as a function of theta, times e to the power I k dot r divided by r. So for this special case, spherically symmetric potential, the scattering amplitude will be only function of theta, not phi. Here theta is the angle between the scattered wave vector k and the incoming particle wave vector k naught. Now, what is the relation between the differential scattering cross section d sigma d omega and the scattering amplitude f as a function of theta comma phi? The relation is d sigma d omega equals to k by k naught times mod square of scattering amplitude, that is f as a function of theta comma phi. Here k is the magnitude of the scattered wave vector and k naught is the magnitude of incoming or incident wave vector. Now for the case of elastic scattering, where the momentum and energy conservation holds, for that case k will be equal to k naught. So for the case of elastic scattering, d sigma d omega equals to mod square of scattering amplitude, that is f as a function of theta comma phi. Now we'll discuss about a approximation in scattering theory, that is first Born approximation. So what does this first Born approximation tell us? This approximation tells us if the scattering potential or the target potential V as a function of r vector is weak enough, or we can say the incident particle energies are larger enough than the scattering potential, then there will be slight distortion of the incident plane wave. In such case, we can approximate the scattered wave as plane wave. We have discussed the concept of scattering in quantum mechanics in details, and we found that the first Born approximation is valid for option A, that is large incident energies of the incident particles and weak scattering potentials.